Okay, let's go ahead and get started. We are in the laboratory today, but this is a dry lab, so we won't need chemicals or Bunsen burners or anything like that. But what we will need are these spheres. The spheres that I'm going to be using are colored to show a little bit more clearly the structures that we're going to need to see. But the styrofoam spheres that you use may or may not be colored. It really doesn't matter. Just follow along with me and you'll be just fine. You'll also need some toothpicks. Again, mine are of assorted colors, but if yours are just regular toothpicks, that will be just fine. You're going to need a periodic table to determine the number of valence electrons that each atom has. You're going to need an electronegativity table like the one I've got here, or if you don't have one loose, you can just find one in your book. There's an electronegativity table there, so you can just use that. So let's go ahead and get started. Let me get these spheres out of the way so we'll have some room to work. But we're going to start with the simplest compound or molecule that is in existence, and that is hydrogen gas, or H2. Now, hydrogen is composed of two hydrogen atoms, and each one of these hydrogen atoms brings one valence electron to the electron dot structure. I need the electron dot structure to help me to understand what the three-dimensional structure of this molecule looks like. And so I go to the periodic table and find hydrogen in the first column, and that tells me that hydrogen has one valence electron. So each one of these two hydrogens has one valence electron for a total of two valence electrons to go into the structure. Well, that's precisely the number of electrons necessary to form a covalent bond, and that's what's happening. There's a covalent bond between these two hydrogens, and so I'll draw those hydrogens in those electrons in right now. So one electron there and one electron there, that is the bond. Now, most atoms will require an octet of electrons, but hydrogen is an exception to the octet rule. It requires only two. So that's a very plausible electron dot structure. It's going to help me to understand what the shape is like. And so the shape is going to be like this. I've got this one pre-made for us. Hydrogen here, with a covalent bond in between. Now let's talk a little bit about the electronegativity difference. Remember, electronegativity is the pull, or the tendency of an atom to pull electrons towards itself. The electronegativity for hydrogen from the electronegativity table that I see here is 2.1. So this electronegativity, the electronegativity of this hydrogen is 2.1. The electronegativity of this hydrogen is 2.1. The difference in electronegativities is exactly 0 then. There is no difference in electronegativity, and therefore this bond is what we call nonpolar. There is no predominance of electrons on one side overall, or net, on one side of the bond or the other. There's no increased, for example, electron density on this side or on this side, and we call that a nonpolar bond. Now remember what polar means. If you think of the Earth, for example, the Earth is a polar planet, meaning that there's a North Pole and there's a South Pole. But here it's perfectly symmetrical. This bond is perfectly symmetrical, and therefore the bond itself is polar. Now let's consider the molecule. Well, we've looked at the bond first of all, but what about the entire molecule? Well, you can see that it doesn't matter how I turn the molecule. I can turn it any way in three-dimensional space, and it remains a symmetrical molecule. Because of that, I call the entire molecule, not just the bond, but the entire molecule nonpolar. So the molecular structure is a nonpolar structure. So that takes care of hydrogen. Let's go to the next structure, and the next one is fluorine. So fluorine is composed of two fluorine atoms in the same way, and there are very many similarities between fluorine, diatomic fluorine, and diatomic hydrogen. But fluorine, I can see from the positioning on the periodic table, has 7 valence electrons. That means 7 valence electrons from each of the fluorines for a total of 14 valence electrons in the structure. Again, I need the structure to be able to help me to understand what the shape is. So fluorine, for example, will have 14, and 2 of those 14 will go into simply making the covalent bond between those two fluorine atoms. So fluorine and fluorine have 2 electrons. I'll put in the next 12 now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I'll ask the question, do each of these fluorines feel as though they have the octet of electrons? Feel as though they have 8 electrons around them, because that's the magic number. Well, let's count. 2, 4, 6, 8. So this fluorine has the octet. 2, 4, 6, 8. This fluorine has the octet. And this is a very reasonable then Lewis structure. This is a very reasonable Lewis structure. I can use that Lewis structure to help me to understand what the three-dimensional structure is, and it may look something like this. So it's very similar, as you can see, very similar to the hydrogen molecule, the H2 molecule, in that the two atoms are covalently bonded. It is a non-polar bond. In other words, there's, again, no predominance of electrons on one of the atoms or the other. It's a perfectly symmetrical bond. Now, think of this as a tug of war. And I know all of us have played tug of war as children, but think of this as a tug of war. Now, fluorine is the most electronegative atom on the periodic table. It's in the upper right-hand corner where very electronegative atoms exist, fluorine being the most electronegative atom with an electronegativity of 4.0. So that means that this fluorine is pulling electrons with a very great intensity towards it. I'll use an arrow with a little line like that to denote that. And this fluorine is doing it the same way but in the opposite direction. So the tug of war is a stalemate. The tug of war is not being won by either fluorine. It's perfectly symmetrical. So the bond in is nonpolar, but the molecule is nonpolar as well. So that takes care of fluorine. Let's move on to the next structure, which is hydrochloric acid. Now, hydrochloric acid has some similarities to the last two. The last two were, as we've seen, linear molecules. That's the terminology. That's what we call two atoms that are connected by a covalent bond. And this is no different than that in that regard. Hydrochloric acid is diatomic. In other words, there's two different atoms, but they're not the same. They're not the same. And so chlorine, in this case, contributes 7 valence electrons. I know that because when I go to the periodic table, it's in the second to the last column, the 7th column. So seven valence electrons coming from chlorine, only 1 from hydrogen for a total of 8 valence electrons. Let's place those electrons. Well, 2 of the 8 are going to be necessary just to form that bond between hydrogen and chlorine. But we have 6 more to place. Don't place them around the hydrogen. Remember that hydrogen doesn't require the octet. The chlorine does. So let's place those around the chlorine. 1, 2, 3, 4, 5, 6. We'll ask the question, does chlorine have the valence of 8 electrons around it? 2, 4, 6, 8. Indeed it does. So chlorine is happy. Hydrogen doesn't require the 8 electrons. It requires only 2. So it's perfectly happy to have only 2. The structure then, again, like the hydrogen molecule and the fluorine molecule that we just looked at, is linear once again, but this time there is an electronegativity that's larger than 0.3. Remember that 0.3 is the number that delineates between nonpolar covalent and polar covalent molecules. In this case, the chlorine has a greater electronegativity. The electronegativity is above 0.3, making this a polar bond. So let's take a look at that molecule. I'll position it like this, but remember, it will orientate itself in space in every possible orientation, but I'll place in the direction that with the hydrogen on the left and the chlorine on the right, so you can correlate it to what you see on your paper. Hydrogen has an electronegativity of 2.1, chlorine has an electronegativity of 3.0. The electronegativity is 0.9, larger than 0.3, and therefore this is a polar molecule. The predominance of the electron density is on this side of the molecule, this side of the bond. It's not an equal distribution, making the bond a polar bond. But the molecule is also polar. In other words, the 2 poles of the molecule are not the same. This is a different type of end than is this, and because the molecule is not symmetrical, if I can imagine then, for example, a line right in the middle of that bond, certainly what you see on this side is not what you're seeing on this side. That makes this a polar molecule. It doesn't really matter which way I turn it. It's a polar bond and a polar molecule with the electronegativity or the electron density towards the chlorine. So that's hydrochloric acid. Let's take a look now at water. H2O is a very interesting molecule in that it is composed of 2 different elements, but not in a 1-to-1 ratio, rather than in a 2-to-1 ratio, 2 hydrogens to 1 oxygen. Now, hydrogens, as we now know, will bring 1 valence electron to the molecule each. There are 2 hydrogens and therefore 2 valence electrons coming into the structure from hydrogen alone. Oxygen will bring 6 valence electrons because it's in the 6th column, the 6th main column, and therefore it will bring 6, for a total of 8 total electrons in the electron structure itself, or the Lewis structure itself. Let's place those electrons. Well, 2 of the 8 we'll have to use just to form this covalent bond right here between the oxygen and the hydrogen. Another 2 we'll have to use to form that oxygen-hydrogen combination, that covalent bond. But we've got 4 more. Where do we place them? Again, don't place them on the hydrogens. The hydrogen does not require the octet. We'll place them here. 1, 2, 3, 4. And now we've placed all 8 electrons on the Lewis structure. We'll ask the question, does the oxygen contain the octet? Indeed it does, 2, 4, 6, 8. Hydrogens don't require the octet, so we have this structure here. Now let's translate that electron dot structure now to a molecule. So let's take a look at this right here as the structure for water. And it's, again, interesting because of the fact that I'll position oxygen in the middle. We'll say this is the oxygen, and these are the 2 hydrogens. Now, what's happening up here? Well, what's happening is that the oxygen, in addition to being connected or bonded to the hydrogens, each of the hydrogens also has 2 lone pairs of electrons. 2 lone pairs of electrons, one here and one there. Now, those lone pairs of electrons are influencing the molecular geometry. Even though they're not bonded to anything, even though these 2 lone pairs of electrons, or these 2 pairs of electrons, are not bonded to anything, they are influencing the geometry. We have a mnemonic to remember, and that's VSEPR, for valence shell electron pair repulsion. I know that's a lot to say, but if you just remember VSEPR, I think you'll be okay. VSEPR, or valence shell electron pair repulsion theory, simply states that electrons, being negatively charged, are going to push away as far away from each other as possible. So if you think of these electron densities, this one, this one, this one, and this one, even though they're not bonded to anything on the top here, even though they're not bonded to anything, if you think of these electron densities as being pushed out as far away from each other as possible, it creates this structure here. And for obvious reasons, we call this structure the bent or angular structure. The bent or angular structure. In a little while, we'll look at to see what happens when we put atoms here and here. But for right now, we call that bent or angular. Now let's talk a little bit about electronegativity. In fact, let's look at this bond right here. This bond between oxygen and hydrogen. Well, the electronegativity of hydrogen, we've already said, is 2.1. Oxygen is much greater, 3.5. So the electronegativity difference then is 1.4, obviously much greater than 0.3. So this is a polar bond. Well, what about this one right here? Also, it's exactly the same bond, so it'll also be a polar bond with an electronegativity difference of 1.4. So, what's the structure? It's a bent or angular structure. This bond is polar, this bond is polar, and the molecule is polar. As you can clearly see, there's a big difference in electronegativity or electron density here versus on the top of the molecule. I'm going to put this down for just a moment, but if I look at the molecule itself, or the Lewis structure, I can see that there's an electronegative part, what we call an electronegative part, on this side of the molecule, an area of high electron density, and an area of lower electron density down here. That's a little delta sign, delta negative, delta positive, denoting those areas of electron density. So the electron density is concentrated here and deficient down here. And so the molecule itself then is what we call polar. The molecule is not symmetrical, it is polar. So that's water. Okay, let's take a look at ammonia. Ammonia has the formula NH3. And NH3 with 1 nitrogen and 3 hydrogens has a total of 1 electron or valence electron from each of the hydrogens and 5 valence electrons coming from the nitrogen. It's in the 5th group on the periodic table. So I have to account for 8 valence electrons, or 8 electrons, in the Lewis structure. How do I do that? Well, I'll need 2 here, 2 here, 2 here, just to form those covalent bonds. But that's only 6 electrons. I need to place 2 more. Where do I place them? Well, don't place them on any of the hydrogens because they don't require an octet, but nitrogen does. So I'll put 2 more electrons, 1 there and 1 there. So let's take a look at the total. I have 8 valence electrons, 2, 4, 6, 8 valence electrons. The central nitrogen has 8 octet, of 8 electrons around it, or an octet. So it's a very viable electron structure. Let's convert that structure then into a 3-dimensional model. And I think this is pretty close, okay? This is pretty close. So we have nitrogen in the middle, that's the central atom, nitrogen in the center, and we have 1, 2, 3 hydrogens in the periphery. But notice the lone pair affecting the geometry. The lone pair causes these atoms to be pushed down in this downward position here, creating a trigonal pyramidal. Trigonal because there's 1, 2, 3 hydrogens attached to the central atom. Pyramidal because it forms kind of a pyramid, all right? Just kind of a tripod like that. So trigonal pyramidal is this structure for ammonia. Let's take a look at this bond. This bond right here is a polar bond because the electronegativity difference between nitrogen and hydrogen is 0.9, obviously bigger than 0.3, so it's a polar bond. These other two are identical to that one, so these are polar bonds. In addition to that, the molecule is polar. The molecule is polar. Nitrogen is more electronegative than is hydrogen, and so there's an electronegative end here on top, an electropositive end on the bottom, or what we call the bottom. Of course, there's no top and bottom, of course, in a 3-dimensional structure for a molecule because molecules move in every conceivable orientation. But nonetheless, we can call this top the electronegative part, this bottom the electropositive part. There's no balance, there's no symmetry to this molecule, and so the entire molecule we call polar. We call polar. All right, and that's ammonia.